mine. I can only ride the ranches once.
It looks like it's still going. Well, you're not sharing screens.
I'm not sharing screens?
Oh,
Yes.
Okay.
Yeah, we're good.
It turned to the play thing.
Yeah, who knows?
That's weird. That's just a glitch.
All right, you guys ready to start?
Yes.
It's Monday. If somebody could shut the door, please, that would be good. Okay, so today we're talking about physics, something that everybody likes to avoid talking about. I see people cheering in excitement. Richard, would you like to comment on that?
Physics engines are awesome. They make life simple.
How many people think physics engines are awesome?
If you make them yourself.
If you using somebody else's physics engine.
Yeah.
So
I've tried to do that. It's hard.
it is. It's tough stuff. I mean, to do basic collisions and things like that is not so bad. But chances are, in the real world, you're going to be using somebody else's physics engine, like a Havoc physics engine or a Farseer or something like that. In fact, I had one of the graduate students, I don't think he is in here right now, but said, hey, it's not fair to us graduate students that, the graduate students have to do all 7 assignments. Aren't you glad the graduate students have to do all 7 assignments and you don't have to, right? But what is that 7th assignment there for you? Why is that 7th assignment important? It's a makeup assignment. Then I thought, you know what? How about having the physics engine, something using the Farseer as an option for a replacement? Not you guys. I know you're saying that. I'd be all for that. Damn, why does he tell us now? No, you guys, it doesn't qualify. If you're using for a physics engine already. But yeah, the Farseer physics engine, there's like a Hello World or something there that has a little ball or something that lands on a platform. And that's cool, but then I thought, wouldn't that be cool if we could change that to Peggle?
Ooh.
That wouldn't be hard.
Huh? It wouldn't be hard, right? You just add some extra stuff. So I think maybe what I'm going to do is write up an 8th assignment, if you want to call it that says, okay, if you want to get into physics engines, here you go, here's your chance. If you're not doing this stuff, I question why. You need to be exploring it. This ties in with our discussion. I used to hire people all the time. And one of the first questions, it was a mobile company, and we're doing some gaming-related things and media-related things. And if you're going to hire a mobile developer, what are you looking for? If you were going to hire somebody, let's say you're going to pay them about $110,000 a year, what would you ask them?
Every phone in the market, how it works.
Do you think they know how every phone?
No.
They don't need to know.
What do they need to know?
How to program.
How to program? Yes. Programming is good.
Limitations.
Project management, no.
Limitations of phones.
How about this? The first question I was asking, oh, you're a mobile programmer. Let me see an application on your phone that you programmed. Hey, how about that? You would expect mobile developers to have an application that they've written on their phone. And if you're not doing these things outside of class, I question, what are you doing? You should be writing games that are outside. It's like, oh, I want to toy around with this. At least do some cursory introduction to some of these things. And so I think next semester I'm going to force people to work with physics engines. You know why? Because it's good for them? No, because they're scared of them.
Yeah.
I'm dead serious. They're like, I don't think I'm good enough to work with the physics. No, it's not that bad. And if you're afraid of something like that, chances are you're going into the wrong field. Okay? How bad was it getting into the physics? How many people, raise your hand, physics engines? How bad was it getting into it?
I mean, it takes some time. You got to teach yourself, but it's not that bad.
Yeah.
Box 2D was terrible, but once I took a look at
Farseer?
Farseer was a lot easier. The main thing about Box 2D that made it so much more difficult is you have to essentially make your own renderer.
Okay, so here's what we're going to do today. I'm going to try to make it through the physics thing, which I think we should have no problem in doing, and then maybe we'll pull and load and run this little Farseer Hello World tutorial, something like that, just so you can see what it looks like. In fact, maybe I'll have you guys come up and actually explain what's going on. But you're going to see a common theme. So let's get into some of the guts of what physics engines do for you and why they're so cool. I think you've already seen that in some of the demos that the teams have come up with, and you have an idea about what these things do. But under the hood, you're saying, oh, well, why don't we write our own? No, you will never write your own. You know why?
No.
I know because I tried.
What you produce will probably suck, okay? And it hasn't been optimized. You have to understand what goes into a physics engine nowadays are 100 people's different PhD dissertations, and they've optimized things, and they have it clever, and they've worked on all these different algorithms. I mean, you think about some of the more complex things that they do with clothing, and who was it that was shooting the grappling hook? Okay, so how would you write that?
Actually,
Yes.
on my own.
It's doable, yeah. I mean, you could probably hack some stuff out, but think about it. It's just built into the physics engine. So why not go ahead and use some of the things that are already there? So today we're going to be talking about mathematics, a little bit of mathematics, not so deep there, collision and physics, and let's just get into it. This is the Havoc engine. Have you ever heard of Havoc?
Yes.
If you've played any video game, you've probably seen the Havoc engine. What other engines are out there?
Unreal.
PhysX is another big one. That's an NVIDIA one. Who else?
Unreal.
Unreal? Okay.
We could just go with Source.
Source?
Source is common, sort of.
What else?
What is the Half-Life 2 in?
That's
It's Source, yeah.
it's all source.
All Source. Okay, let's just get into it.
Oh, you
Or maybe
clicked
not.
out of it.
Let's try doing that. Okay, so here's the basic problem. Without physics in your game, what is your game?
Not a game.
Right?
It's a space shooter, essentially, right?
Yeah.
But is it really a space shooter? Well,
There can be a lot of things.
You can't move.
there's a lot of things that are not there that are expectations of games nowadays, right? So there's no gravity. There's no concept of gravity. In fact, a lot of you people, a lot of you folks that are writing these games may not have the concept of gravity in your game. That's okay. I mean, it depends on the game that you're writing. But yeah, there's no gravity, there's no friction, there's no collisions, right? So you have to write your own collision detection methods. And objects are going to pass through one another. In other words, it's going to be this giant kind of jumbled mess. Okay? So we have to determine a couple of things, such as if the objects collide. We'll talk about a couple of different approaches that you may not be aware of. And then we also have to determine when and where they collided. So this is called collision resolution. Okay? If we were going to determine, let's assume that we're writing our own physics engine, and we needed to determine if collisions had occurred, what would you do?
Check everything.
Check everything. Keep going. Check.
Check if everything is colliding with everything else.
Okay, check if everything that's collidable is colliding with everything else. How efficient is that going to be?
None.
ON squared.
O(n) squared. What does that even mean?
Really bad.
You should have seen this thing right here, right? Naive algorithms, and that's how you spell naive, by the way. That's one of the only chances. Is that French?
Oui.
Is it?
Probably.
I think so.
It's
Okay, we'll say that it's French. I really don't know. But anyway, it runs in
Italian?
n squared. What does that mean? It means that for every object that's in this scene, it has to check against every other object. So for one object, it has to check against n minus 1 objects that are there. Am I done?
No.
No, I need to go to the next object and check it against every other object. So it's this n squared algorithm. You can see that that thing is not going to be very efficient, especially when you're trying to run at 60 frames per second. So do you see the basic problem, right? If you write a naive physics engine, it's probably not going to work well once you scale this up to 100 objects. How many comparisons in 100 objects?
10,000.
10,000 times 60 frames a second.
600.
I was watching Futurama, so I can probably cut this out. Do you know, if you haven't seen Futurama, it's okay, it's in the future. This guy goes forward 1,000 years, and in his bank account in the year 2000, something like that, he had 98 cents. Compounded over time, 1,000 years later, do you know how much money he had?
It's like $8 billion.
Yeah, like 4 or 8 billion, something like that. If you do the math, you'll figure it out. It was actually, we calculated it out at 3% interest as $8 trillion, actually. So they were off Futurama.
By a lot.
By a lot, yeah. But then again, who knows what the inflation rate is. Okay, so anyway, we have different situations that we have to worry about. Bullets, of course, are very fast, right? All of these projectiles that are flying through the environment. Characters are also really complex. Why do we say they're really complex? We're not talking
Lots
about
of
their personality.
parts.
Look at different places they should be colliding.
Think about all of the polygons and all of the vertices that are inside this character that we have. So they're really complex in that sense. We have two primary methods that we're going to use for collision detection. One is overlap testing. This almost sounds like a test question, doesn't it? How about that? And then also intersection testing. So let's go ahead and dive into those things. Okay, overlap testing determines if two objects. So how are we going to do that? Okay, this one is going to be the one that exhibits the most error. You're going to see why in this next slide. It's also discrete. What does that word mean?
Ones and zeros. Or no.
It's not continuous. What does that mean? Go ahead, just anybody.
It goes by the simulation steps of the physics
Time is stepping forward. Now, when we talk about is time continuous,
Sure.
this is not a deep theoretical. Is time continuous? Absolutely. It's a continuous kind of thing, right? Because you
far
can
as we
keep
know.
dividing and you can just go infinitely down to some exact moment in time, but then you can divide that, right? It's infinitely precise versus what these physics engines actually do. Okay, these are discrete physics engines, meaning that you step them forward by some fraction of time. Why is that so problematic? Why am I belaboring this point?
The main issue with the discrete steps in time for a physics engine like that is that essentially in between frames something can pass through something.
Yeah, there's all sorts of problems. There's ramifications that come from this. Did you have a comment also? Or
Yeah, you have like a bullet flying around Mach 2, and you're like calculating its position every 60th of a second. There are gaps in between.
Yeah, it can pass right through a human. In fact, you're going to see that. You shoot somebody like, hey, I know I got a headshot on that guy. And the guy's still running around all happy, everything. But no, that's not the way it works. Okay, so that's why we're saying it's discrete, meaning that you're going to have these well-defined sequences that occur with regard to time. Okay, the results are going to give you a time of collision. Say this collision occurred at this time, and also give you a normal of collision, which we'll have visualized in just a second. It uses this technique called bisection. Let's see if you can figure it out from this graphic. How does this work? We have time 0 and time 1.
Well, I read the book, so I already know.
You know. You shut your mouth. You read the book.
Yeah, basically what it does is...
Wait, I'm serious. You read the book?
Yes.
You get a marker.
That's for you. What's your name?
I'm Thomas.
Thomas. Thomas, that smiley face is not you. That's me.
It's very useful as well because it really linked in with the work I'm doing in the Farsi.
Are you saying that reading is useful? I'm not making fun. I'm just blown away. Okay. Go ahead. Tell me what's going on.
Essentially what it does is once it actually detects with the regular discrete setting of time, like once a certain frame passes, it detects that a collision's happened and it's still overlapping.
Yeah, be careful, right? If it detects that it's going to occur in the next time step.
Yeah, in the next time step. Then it'll essentially start cutting down the frames into halves. And it usually takes about 5 iterations. So for the next, for a half frame step, then if it's still overlapping, and it keeps on going backwards to see what the closest approximation is that'll have the circle just on top of the box that's actually landing on the box, not landing.
So to paraphrase what he's saying, right? Time 0. This is one frame. Update is called again. It doesn't really matter how this event has occurred, but imagine that we can advance time and we determine in that next frame that we have a collision. How do I know? Because, hey, you've got a circle inside a square. Everybody with me? Okay, so we've detected that there's some kind of collision. I need to resolve this collision. I need actually to back this thing out because this is no good. Right? So I need to back this ball out so that the ball is actually touching this cube if we're in 3 dimensions. This is a 2-dimensional picture, but bear with me. Okay? So I want to pull this guy out. How do I do that? Actually, I'm going to back it out halfway. Why is halfway such a good thing?
Because it's easy to good math.
It's it's got to be somewhere. You're dividing in half and dividing in half the distance between time 0 and where it is at time 1. So look, we pull this sphere out. We still have a collision. So what do we know?
It's before that's still.
Yeah, the collision occurred before that, so I'm going to back it out a little bit more at t at 1/4 second, or t, whatever this evaluation is. So 0.25, 1/4 of the distance between t0 and t1. Now I don't have a collision, so what do?
So forward.
I go forward how much?
Forward.
Half of a quarter is? A duck, right. So yeah, you can see it's 3.7. So we're constantly dividing by 2, the amount that we're going to do that, and eventually we get pretty close. We have a little bit of collision here in this, 4th, 5th picture, something like that. And you can see that there is some error there, but it's close enough. Do we care? Hey, the bullet should be touching the guy's head as opposed to it being, out here. How many do we want to restrict this to? Are we going to ever be exact? No. You cannot be exact, right? Because this is a discrete system, so there's no way to be exact. But I think you get the idea. This bisection is this half and half. Once you've detected that future collision, you're going to back it out and keep and eventually lock in where you're supposed to be.
So what happens if it's going so fast that in between two frames?
See, that's what the
You mean like this?
Yeah.
Peter asks a great question.
That's
What
what
happens
the
if you have this situation?
well,
It passes.
Screw it.
they'll never notice.
I like that. I don't want to play any of
It's a
your
feature.
cards.
That's what the other method of the intersection testing allows you to essentially prevent from happening.
Yes, right, so-
fits extensions like Farseer, you have variables for if full or if not, and that changes the way that it solves the equation.
Could we still do something with this situation? How do I know that I've passed through? Yes, Chad.
We can basically take the velocity of the bullet and figure out how big that gap is, and then check if there are any collidable objects close enough
Yeah, that is
to
what
where
the
they could be in that
You
gap.
want to do it before it goes through. You just check the trajectory.
Okay, so similar to what we saw before, right? I know that at T0 on here, at T1, I'm on the other side, but there's no collision that I've detected. What could I detect, though, to know that I have a collision?
That line.
Yeah, like have a ray.
Well,
How about which side of the polygon I'm on? You think about it, because if we know normals, we know positions, all that kind of stuff, I can say, you know what, I know at T0 I'm on this side of this polygon, and at T1 I'm on this side.
there's a slight problem with that. You're getting into like you have to know the faces of all the objects that are around. Yeah.
Okay, no, but it's still computationally possible, right? So, I mean, if you wanted to look at it mathematically, you can pick any of these points right here, it doesn't matter. Have a vector come from this vertex to T0, and you also know the normal of this plane, versus on this side right here, take the same vector from this vertex to T1, and you're going to figure out that the angles are going to be negative from one another, if that makes sense. Yeah? So it's still possible to use this, it just becomes really computationally expensive. Or what could you do? I could make sure that nothing is thin in the environment. To say that the speed, in fact, I put that down here as a design constraint. Let's say that you have some really crappy physics engine. The speed of the objects times its time step has to be less than the size of all the objects.
I've actually, when I was designing my own physics engine, I ran into that, and I did.
And it happens, right? It's a real problem. Okay. So to solve this, there's also something called intersection testing. Some physics engines use this as well. Okay, so you can imagine that we're going to smear this object across time. So here you go. At T0, we're over here on the left-hand side. At T1, we've now moved over. And so we've created this volume here that's really a capsule, right? So between this sphere and this sphere, or whatever, we've now smeared this thing across. And so we're doing this sweep. The nice thing about this is if you look down at this picture here on the right, look at time 0 here. Excuse me, between P1 and Q1, and then time, the next time step here, Q2 and P2, how do I know that I've had a collision? Because at this time step here, they're on the left-hand side. At this time step over here, they're on the right-hand side. How do I know that the collision has actually occurred? There's something here on the screen that tells you a collision has occurred.
All the capsules will overlap. Capsules of the
Well, the lines intersect.
yeah.
Right, so if I'm looking at this right here, you can see that I have two non-parallel lines, and these are line segments, right? So you have to be really careful. I'm only checking to see if these line segments intersect, and if they do, therefore I know that I have some kind of collision.
Well, assuming that velocity is not.
Yeah, well, but remember, this is a time step.
We're looking at something that is moving probably about the same speed.
Right, so remember, these are line segments too. So if Q1 was going really slow, and let's say it's line segments only here, it would never intersect with something that's really moving on. Okay. It's a good thought, though. You'd be a great tester. Okay, we also have something called Minkowski sums. These are great, wonderful kinds of things. Almost sounds like a test question, doesn't it? Have I told you all of the things that are going to be on the exam? Probably. Probably.
Everything.
Generally, yeah. But I mean,
It's hard to know what to study for.
some people have read the book. I'm going to bring that point up. In fact, I don't think I'm ever going to forget the name Thomas. I remember back in 2013, we had these textbooks, and one of the students actually read it.
And so we knew it was on the
And he liked it.
presentation before he actually even showed it.
Okay, so we get to Minkowski sums. Watch how these things work. It's another way to simplify the process of determining a collision. So if we have this sphere or circle x and we have a square y, and I'm going to build this Minkowski sum, what I do is essentially take this sphere and I move it to all possible positions where a collision could be. So if you look at the Minkowski sum, it's this third image here, this XOR, or whatever the heck that thing is, y, and I get this bounding volume that looks kind of like this. Right? Now, why is this so important? Because I can use it later on as this sphere passes across this. I simplify this so that I'm not really checking to see if this capsule collides with this square. I'm looking to see if a line collides with this square. Or this sum, actually, this Minkowski sum. So it makes things considerably easier when I do something like that. But what does this imply?
You have to pre-calculate.
You have to pre-calculate everything. You have to basically move this object all around, and do the combination of these two objects stuck together and all the different possibilities. And once you have that, then you have this big blobby kind of thing. Yes?
But it can be very useful because if you have like 1,000 bullets, then you only need to perform that pre-calculation once.
Yeah, the pre-calculation is done
for all the bullets.
Have a loading screen.
And this does work in 3D too. I think if you look at the schedule, you'll see a couple of links that'll show you really funky looking kinds of Minkowski sums in 3D. If you want to see what that looks like. It's almost like they take a little rabbit and they say, okay, we're going to do this Minkowski sum, and then it makes the rabbit look like he has some kind of disease because he's all like bulged out and nasty, scary stuff. But there you go. Okay, now practically speaking, how these things are implemented, they usually do it one of two different ways. We have AABBs, and we also have OBBs, right? AABBs, you actually see this in the physics engine's documentation. They're called axis-aligned bounding boxes, right? Just making sure I got that term right. What does that even mean, axis-aligned?
X, Y.
Everything is relative to the X, Y, and Z axes, right? What do you get? You get something that looks like this, a nice, perfect carton-looking kind of thing. Versus this right here, oriented bounding boxes. So you can see that it's oriented to the rotation or the orientation of the model that you're talking about. Very cool, right? We have a lot tighter fitting container around this rocket, but what's the problem?
There's still points that will show up like you hit the rocket, even though, especially in the front part where the nose is, you'll see where it will be like, oh, you hit it and you didn't really hit it.
Well, that's true, but it's tighter than this. It's still better than the one on the left because if you look, the rocket's aimed up here to the right. Look at all this whole section right here. That's a little bit off, right? So at least the oriented bounding box is better. Yes?
Is it more processor intensive?
Much more processor intensive. Why?
That's tilted.
You have to worry about the rotation. Yeah, now we have to worry about these rotated points and everything else. And so if you're trying to do the fastest implementation, you would go with these AABBs, the axis-aligned bounding boxes, right? If you're trying to get more precise, then you can potentially use this oriented bounding box. Right? What is the bounding box even used for? It's a collision detection. And why are we trying to reduce it down to something that's in the form of a box? Simple. Yeah, boxes are easy. You guys could write the code. All you have to do is test to see, is a point inside this box? In fact, that is one of the questions that a lot of employers in game design do. They say, oh, go write a function that determines if a sphere has collided with a square.
So many options.
There are, but just realize they are going to give you a coding exam. It could be something like this. Determine if two squares overlap. How would you do that?
No, you wouldn't use distance for that. That would be spherical.
I would start thinking about this. Maybe we should come up with a whole bunch of questions and say, let's see where you stand.
That sounds like fun.
That sounds like fun?
Yeah.
Sounds like a good experience.
Yeah, okay, we'll talk about that later. Yes, you had a question.
So which is more computationally efficient, a bounding sphere or a bounding box?
That's a great question, too. You guys, I don't know if you've read the slides before you came in. That kind of takes some of my thunder away, but there you go. So which one is the easiest? Right, so if we're going to do any kind of collision detection, what is the easiest thing to calculate?
Sphere.
Spheres. Why?
It's just a radius.
It's just distance. Square root of x squared, delta x divided by delta z. You've seen that thing before, right? So that's the easiest one. Computationally, you might be able to get away with some other things. You might be able to get rid of this square root aspect if you do some other kinds of things. And then, yeah, you could use the bounding boxes. Those are another easy one. Next one is a capsule. What is a capsule?
Semi-sphere with
Yeah, it's just two
cylinder.
spheres separated by distance, and if you look at the math, that's not so bad. The next one are the AABBs. Why? There's more points to check. Right? Think about it. There's just more points. Okay, and then what can we do about character collisions?
Multiple.
I think we had talked about this before, but let's assume that we're making a fighting game. If I was the anal retentive kind of person you think I am, and I was going to make the fighting game, what would I do? I would punch and I would check every single polygon inside this to see if there's any kind of hit. Is that feasible? There's no way that's going to happen. So what do you do as an approximation? Yes?
Hitboxes.
You can sort of have a bounding box for each individual parking lot.
Giant bounding boxes, exactly, right? So you can imagine there's a bounding box around the head, so you don't have to do all of that complex kind of stuff. There might be one around the entire chest cavity, one around the legs, something like that. Yes?
Would that box change shape if, let's say if you have a hand and there's a box on the hand, it would change shape if they close?
That's a great question, would it?
Have you programmed?
It's a good discussion question. He said, basically, imagine that you've got a hand that can move. Would the bounding box change shape?
Yeah.
It should.
If you wanted to.
If you want it to. That's the answer I was looking for. Do you know why?
Because anything is possible.
So imagine that you're the one who said let stuff just go. I'm not. So imagine that I've got the two-finger death eyeball punch, and Matthew is my foe. And I stick those fingers out like this, and I shove them into his eye sockets and then kill him that way, right? Do I care then? Probably, right? Because, if you're doing some kind of close-up something or other. But for the most part, people are so far away from each other, it doesn't matter. If I go like this and I'm within a foot and it looks like it hit him, most people don't care. You're not looking for pixel-level precision or vertex-level precision for most games that you're working with. I don't think that anything is really using that.
Like a Street Fighter.
No, probably not. I mean, there are some per pixel algorithms that you could do. In fact, somebody I think in here was looking at that, but it's something out there if you want to see how it's implemented. That code is available.
Well, and even per pixel collision detection isn't always the best because let's say that you're standing next to a spiked wall and you just stick your hand out, die.
You're talking about it in real life, or? I certainly hope.
Well, you take damage, but you wouldn't die.
Yeah, but realize there are a lot of options when it comes to how you're going to detect collisions. Bounding volumes are one. It's a good approximation. It's relatively fast. Okay, so how do we get rid of this n squared thing we were talking about at the beginning of this lecture? Well, if you look over here on the left-hand side, there's a way that we could divide up all of the objects that are in the scene based on the space that they're in. So there's like binary space partitioning. There's all sorts of different kinds of things. But watch why this is so good. If I have everything in this grid or cube kind of, Rubik's Cube kind of format, what can I then do? What do I know about this guy that's in the upper right who's going down?
He's going to be in that room in that corner.
Is he going to be colliding? And I don't know why it's a he. Actually, isn't that the symbol for a woman?
It does have a cross, though.
Oh, it has a cross.
There's a cross. There's a cross.
Meanwhile.
Oh, no, okay, so this one right here is a god, right?
Yeah, that's a guy.
It doesn't matter. But I do know that the thing, whatever it is in the upper right-hand side, is not going to collide with this guy right here. How do I know that? Because they're all the way across the space from each other. So it makes sense that we can call things down and only check neighboring cells as opposed to doing this naive, I'm going to check everything against everything. There's no way that your physics engine would run in any reasonable amount of time if you did something like that. So does that make sense? Okay. The other thing that we can do here, and this one, when I first saw it, I've never done anything like this. It's called the plane sweep. Okay, and if you're trying to read the book, in this case, pay attention to what's going on. I'm trying to detect if this rocket is intersecting with the circle B. Is it? Yes, clearly. What they're saying is that we can organize the coordinates of these things. You can see these two red lines here for the rocket. So this is the minimum, let's say, x value. Over here on the right side, this red line is the maximum x value. Okay? And I can do the same thing for the y values here of this sphere, something like that. Basically, if you have two of those lines cross, you know you have an intersection. I want you to convince yourself of that, because think about it. Do I have a collision with A? Does this rocket collide with A? Clearly not. Why not? If we were to do the same thing here that we did with B and I did with A, what would be the problem?
The minimum x value for the rocket wouldn't cross. Never mind.
The maximum value, the maximum y value, or I'm sorry. Yeah, so basically imagine sliding these two green lines down so that they encompass A. How many collisions, how many lines are crossing there?
None. Mine's are
One.
There's one.
One green line from A crosses R.
Do you see it? If everything is sorted, that's the assumption that you have to make. If we're sorting all of the x and the y values, then we can do simple comparisons to say, look, if in this case the minimum x of the rocket is still greater than the maximum x of A, then we know that there's no way that they can collide.
So you don't even have to show.
You see? Yeah. So it's all based on sorting. What's the problem with that? You have to sort. Yes?
In the book, I really couldn't, they didn't say any negative consequences of planes with what are the negative consequences.
What do we have to do?
sort.
Sort.
Right algorithm.
What sorting algorithms are you going to use?
Random sort.
It should never recommend bubble sort. I think bubble sort is good if you have less than 10 elements or 7 elements or something like that. It's in one of the constants there. Yeah, quick sort is probably good. If you have a lot of things that are in the scene, you want to go with an n log n or even an n. There are a couple of n's that you could use, order n algorithms. Okay, and then we get into terrain collision. Now, how is this? Look at the nastiness of this mountain system right here. You're thinking, oh my gosh, how am I going to detect if there's a collision? What could you do? A bounding box? AABB? What's the problem with AABBs? You think about it, you'd have a bounding box that's at the height of the mountain, the tallest mountain that's there, and you'd have, I mean, it just would not work. So what can we do? Well, a lot of these terrains are actually made off of something called a height map. Do you know this term? How does a height map work? It's a grayscale. You guys are saying black and white, but it's a grayscale image. It's a picture. Or you can think of it as a picture. What do we do with that? Did you guys see me? I think I did this. I did this Unity demo, right?
Yeah.
How did I make the terrain? I painted, right? So I went over there and I said, shh, okay, I want some mountains to come up, and the mountains popped up. What was I really doing? Okay, in this situation, imagine that we have, for simplicity, a whole bunch of points that make up a 2D grid along the XZ plane. Stay with me. XZ, which way is that? It's flat, right? It has X, it has a cross, and it has depth. So it's the XZ plane, okay? The height map are a whole bunch of values that are between 0 and 1 or 0 and 1,000. Doesn't really matter. But that's going to dictate how high up that point is supposed to be. You with me? Height map, very important. You can hear about height map the rest of your life. So what we can do is we can say, you know what? I know where everybody's X and Z position is, but I don't know where the Y is, so I'm going to look it up in this height map kind of thing, and then I'm going to raise that thing up. Now, why is that so cool? Because it allows us to do stuff like paint images, and we can pull up mountains and everything else, okay? So that's what a height map does. That sounds like a good test question, yes? Okay. So then we have to determine which triangle we're in. Can we determine which square we're in?
Yes.
Let's say we want to determine where this ball is and which terrain it's above. How would we do that?
The terrain block is as big as a
Potentially.
Use X and Z coordinates.
Use the X and Z coordinates of the ball. Keep going.
And look at the height map to see where the Y is.
And then I could look at the X and Z coordinates of
The terrain.
the terrain. You know.
Set the Y to the ball.
So then I can determine which square I'm in. Is everybody cool with me there?
Yeah.
So it's a pretty straightforward process to determine which square you're in, but then you also have to worry about which triangle you're in. And so if you look right here, here's one of these squares from the top-down position. So I'm looking, I'm way up in outer space, let's say, and I'm looking down on this one polygon that's right here that has two triangles. And I need to determine if the sphere is on the upper left triangle or on the lower right triangle. How am I going to do that?
There was some really complicated equations.
There's some really complicated equations, but this is embarrassingly simple. What does this line really represent? Yeah, it looks like it's the edge between, it's X equals Z. People are like, what? Some folks are like falling asleep too. I understand it's a boring lecture. But this line represents where X equals Z. So therefore, what can I do? I can just plug in the coordinates of the ball, the X or Z, it doesn't really matter, and then I can figure out which triangle it's in. Convince yourself. In this case, think about it. It's further deep than it is left.
So inequalities?
Huh?
Inequalities?
Just a simple inequality. It's like, it becomes an if statement. Yeah, if the x of this is less than the x of this or something like that, then there you go. Okay. When we resolve the collision, once we've determined that a collision has occurred, what are we going to do about it? Well, there's 3 different phases to it. There's the prologue. So this says, do we want to ignore that this collision has occurred, or do we want to trigger some other event? What other event might we trigger?
Explosion.
Hey, there you go, an explosion. Okay?
I think that's the epilogue.
Well, okay, yeah, but it's basically what other kinds of events might we want to trigger?
Damage.
Right? The actual explosion and everything else would be a result of that, which would be down here. Okay? Or triggering the start of a sound, something like that, right? So we have to basically trigger some kind of other events. Collision occurs, the objects are moved to the point of impact, new velocities are calculated, normals, all that kind of stuff, and then the epilogue is to do things that are the follow-up of that. So it would be like destroying the objects, do some kind of effects, damage, whatever.
Removing health.
Removing health, yes. Okay? When you work with the physics, I'm not going to get into all of this stuff. Yeah, I'm sorry, go
For
ahead.
the prologue, collision, and epilogue, does that all happen in the same sequence? Like,
I know what you're trying to
same
say.
Coding sequence.
That is going to depend on the physics engine. Because some physics engine are just going to say, you know what, a collision has occurred, deal with it. Right? But if you're breaking it down into its subparts, and you would have something like that, some physics engines may have callback functions that sit there for each one of those things. Say, you know what, I've determined that there's a collision, what do you want to do? Okay, now that there's the collision code, what do we want to do? And then most of the time it's basically just collision has occurred. Okay, but anyway, when you get into working with physics engines, how do you map pixels to feet and meters? How did you do it in the Farseer? Do you guys remember the code?
Was I expected to make like actual legs? Because I didn't end up doing that.
It doesn't matter if you do 3D.
It's just convert to cent units usually.
You have to say things like how many pixels convert to meters, okay? But one of the things to remember is to use consistent units. A lot of times these things have been developed in other parts of the world. Not everybody knows what a foot is, or what, well, not I mean foot, a mile. Why did they pick such an arbitrary kind of thing? 50 to 80.
Because they got dropped one night and said we want to make up units.
I think so.
You go back and look at like rods and chains.
Why do we have 12 hours in a day? What if we only had 10 hours, or 12 hours in a period, 24 hours in a day? Why not 10?
Well, 24 is divisible by a lot of different numbers.
Because the Greeks are weird. I don't know. Somebody look it up. Maybe we'll make the graduate students do that. Okay. But anyway, we get into something
Julius
called
Caesar said
particle
so.
physics. Have you taken particle physics? Yes, I believe you, if as a games major, you should have taken a physics class. If you took the calc-based version, then you have a true appreciation for what's going on, because we know that we have position, velocity, acceleration, right? Are these things related?
Yes.
Technically,
I put it down here. They're either derivatives and or integrals from one to the other. You should recognize this, right? 1/2 AT squared, all of that kind of stuff. It now kicks in, and you understand why the calculus-based physics is so much better. It's probably more painful, but you get it. Okay? All of these kinds of things are in physics engines. Okay? We also have center of mass. What is that? The center of mass. Yes, this is why we simplify things. In particle physics, when you take particle dynamics, I think is the course proper name. Okay, when you take that, it assumes that everything is compacted into an infinitely small particle, right? Is that the way the world works? There's no way. So we have to worry about the center of mass, and you can imagine that this thing is an infinitely small kind of thing. So that would be your particle dynamics. But you can see we have a lot of different ways that we can visualize the center of mass. Okay? I won't get too much into this, but you can see that there are the possibilities just prior to impact, just after collision, and during collision. We also have some weird things, right? So if we have this before collision of two, let's say, cue balls or something like that on a pool table, they're going this way. How do we resolve this? I want you to appreciate how nasty of a problem this is. It looks really simple, right? But if you have two of these things, this one's going this way and this one's going this way, and they have different masses, what are you supposed to do? How are you supposed to resolve that? Weighted velocities. I've tried to do this. I'm like, oh, that's easy. I'm going to write my own little billiards kind of thing. No, fail. Big time fail. Okay? Other definitions that you need to know about when you're working with physics engines. Kinematic objects do what? Move. Static objects?
Don't move.
Don't move. All right. Rigid bodies?
They don't
Don't deform. Okay, and then soft bodies do deform. Okay, so you can hear those terms a lot. But these are those that do. They change their center of gravity. I want you to think about why that's the case, right? If you have a car and a big rig just comes along and smashes the whole front end, what happened?
There's no more cars.
Mess.
There is no center of gravity. It's all over the place.
The mass moves.
The mass moves, right? So it readjusts, and that becomes a really ugly, nasty problem if you do things correctly. Yes?
I just wanted to take note that there is a new physics engine called BeamNG.
Yes, yes, I've seen it. And there's lots and lots of car demos from BeamNG. Yes.
And it is amazing.
Okay, there you go. Has anybody played with BeamNG? If you YouTube that, you'll see it all over the place. There's tons of videos.
How do you spell that?
And it is pretty cool, I have to admit.
They just have tech demos for it right now.
Isn't this ugly?
Very.
Mathematically, I want you to appreciate what these... How many people are interested in writing their own physics engine again? Because you have to deal with this.
Do I want to?
Yeah, that's what I'm saying. It gets into things that you probably don't want to deal with. If you look at this situation, you can see it gets quite complex very quickly. And this is just two things hitting each other, let alone all the other things that physics engines do. Okay? Other definitions. This is one of my favorite things, and I have not coded this up, but I'm dying to do it. There are constraints that we can put on the physics engine. Constraining them, saying, if we had a joint or something like that, right? Can I take this arm and spin it everywhere that I want? No. Good. I couldn't, right? I can only go over so far, and it stops there, and I can only take it so far back. Stop. I see a lot of double-jointed people. Look at me, Jeff. So you're putting restrictions on what the physics engine, what you're going to allow this thing to do. You have hinge joints. What's a hinge joint? Yeah.
RCR has rope joints.
Rope joints.
What? Yes, they do.
Rope?
You have a question, or you good? Just talking physics.
Yeah.
Okay, good. Not Facebook, though. Okay, good. That's even better. Sliding joints. What is a sliding joint? I hate to even ask what you guys are going to say. You can imagine it's something that is constricted to some kind of pole, right? Kind of moves up and down the pole. So there you go, sliding joint. There's also ragdoll physics. Have we talked about ragdoll physics?
No.
Pretty familiar with that.
Okay, then this is where, remind me to come back to this, because I want to end this lecture with ragdoll physics. It's really good for violent death animations. And I have the link right here, so I promise I'll play this. I don't want to record it on the video here, because there's no reason to do that, but I do want to come back to that. Okay, we're almost done. Physics engines that you'll see out there, there's a whole ton of them. BeamNG, being a new one also. There's underwear physics, PhysX, this is a huge one. Novadex, this was in the book, I think, but no, you don't really see Novadex. There's also things like Tokamak, I've used this physics engine before. Bullet is a hugely popular one right there. I don't know if you've seen 2012, the movie. Anybody? Mm-hmm. They used the Bullet SDK for that. I want you to appreciate, the commercial, big-time, $1 million budget kinds of things are using this thing, and it's free. You can download it right now if you wanted to. So Bullet is a really good one. I've used that in a couple of different projects. Very much worth your time. Okay. There's also some demos I'm not going to go through right now, and I think that's the end of that. So let me stop the screen sharing real quick, if I can.